All right, so this is our 9th GBM of the semester. Owen's going to be covering Intro to Heap Exploitation, so Street of Noop. If you haven't already, please sign in. That sign-in is really important because it helps determine your eligibility to vote in our elections next week. And then speaking of elections, if you're interested in either an officer or chair position, please contact me. You can either email me or DM me on Discord or Slack with your statement of intent for running for an officer or chair position. And these are due next week. They're due 11:59 on 4/21, which is on Wednesday. And then elections are 4/22, that Thursday, at our normal GBM time. I have a list of the officer positions available, and then the descriptions are listed on Slack and Discord. If you need any more information or want to ask questions, please just reach out to me, and I'd be more than happy to give you information about the positions or help you decide if one position may be right for you versus another. I highly encourage you to consider running, even if you don't think you have the experience that may be required. A lot of these positions are there to help you grow and contribute to the club wherever you are in your cybersecurity journey. So don't be intimidated, and we can find a right fit for you. So please reach out to me. It doesn't have to be a long statement of intent. Just like a paragraph would be perfect. So yeah, that's the major news item. So with that being said, I'm going to turn it over to Owen so he can get started.
Awesome, thank you. Yeah, you should definitely run for officer positions if you can. I remember when I was like a freshman, I ran for competition and development officer, and at the time I'd done like maybe 5 CTFs or so. I wasn't good at all, but I feel like having that position made me like work harder and learn stuff that I wouldn't have done before. So I'd recommend that to anybody. Trying to find out how to share a screen. I'm just gonna share desktop. I think that's the easiest way to do this. Okay, so can you see my screen? Any thumbs up or downs or whatever? Okay, cool. Can you see like the sidebar with everyone else on it too? I don't know how that works for screen sharing, to be honest. I think it's probably fine.
Yeah, we don't see it. We just see PowerPoint.
Okay, cool. Yeah, I'll get started then. Let me find out how to get started because this Zoom thing is blocking my view. Okay. Yeah, I'll just play it from the current. Okay, so what I'm going to be going through here is it's kind of an introduction to heap exploitation, but it goes into a lot of depth. It's very long, but I try to go through everything and a very good using it for don't normally keep exploits, but if you have any issues, you can send them in the chat, or if you have issues, you can type a message in the chat or use your voice, whatever. Anything works for that. Did I lose my internet connection? No, I think I'm fine. Okay, so I'm gonna get started with it then. Yeah, if you have any questions, you can just shout them out if you want. I'll try to keep the chat open too if I can. Cool. There's the chat. I'm new to this stuff, by the way. I don't do a lot of presentations. Okay, so a sort of table of contents. It's not exactly like this. I changed it a lot after I started, but this is like a general gist of what I'm going to be going through. First, I'm going to be basically explaining why heap exploitation is important and why it's a very useful skill to have. Then I'll be going into the different bins and chunks and how the heap actually works. Then after that, I'll be going into a couple of the primitives, starting with some of the ones that involve memory corruption, and then I'll also go into the different ways you can get leaks on the heap for whether it's heap or libc or whatever you need. Then I'll be going through the classic houses. A lot of those are for 2.23. I have a lot that I start basically at 2.23, and then I sort of go forward from there. I go a little bit into FSOP because for modern heap, you have to do a lot of stuff with file structs. Then I go into more modern attacks, and then for after that, I go into how you can create your own heap exploits, debugging, practicing, things like that going forward. Is this being recorded, by the way? I don't know if I get a thumbs up or something.
Yes, it's being recorded.
Okay, awesome. Perfect. Okay, so first, a little bit about me. I go by Noop Noop online. My name is very easily found. Like, that's not actually like anything that I try to hide, but I'm just not gonna like say it. You can find it if you want. I'm a senior at the University of Florida. I'm the captain of our CTF team, Colonel Sanders. I also do a lot of CTFs with a team called Dice Gang, who's a very strong conglomerate. I do mostly pwning. I do a little bit of reverse engineering, at least enough to do the pwning that I do. That's about my limit for that. And then I'm always trying to find new challenges, whether it be trying to learn kernel, heap, browser. If there's something I don't know how to do, I usually try to find a way to do it because I think it's super interesting to learn new things and have new skills under your belt. There's a picture of some of the people on the team for when we won Seesaw Quals in 2019. That was the first time we'd won since I'd gotten there. It was like my third year in, and we were all very proud of how hard we worked to get there. It's a picture online, so I assumed everyone in it was probably okay with being in it. Okay. So what actually is heap exploitation? The main thing about the heap that people know from doing any sort of C programming or C++, probably other languages too, is that it's used to sort of dynamically allocate memory. And by that, I mean, when you need memory to store a string or an object or a structure, you will call something like malloc to obtain this memory, and then you can use it. And then when you're done, you can free it. And to a lot of people who do C programming, it just kind of happens. I don't think people often question how it works. They just know if I malloc a size of hex 40, then I have hex 40 bytes to work with. I don't want to go over that. And I'll go into why. You could also use calloc, which is basically malloc, but it also zeroes out the memory in most cases. And then realloc is used to expand or shrink the chunks as you need if you have more data than you can currently fit with your current size. Yeah, there's a lot of vulnerabilities in this region of memory though, because it all happens in this weird memory region called the heap. And these vulnerabilities can lead to a lot of really strong primitives. You can get arbitrary reading and writing. And if you have an arbitrary read-write in libc, a lot of times that can lead you to a shell, which is just system bin sh. Sometimes you can read files or do whatever else you want, but you can get code execution. That's all that matters. You get running your own stuff. Okay, so why would you actually want to do heap exploitation? Isn't there buffer overflows and stuff like that? A lot of those are not actually as common anymore. I mean, if you're working on some super old embedded devices made in 1920, then you're probably still going to be able to find some buffer overflows to shellcode, but that's not really as likely anymore. A lot of times there's more GCC mitigation, such as shadow stacks and canaries, that make buffer overflows a lot harder if they even do exist, unless you have a leak or other strong primitives. And also programmers are getting smarter. They're not just using gets anymore. They're not just using fgets hex 1,000 because they don't know how much memory they're going to need. I think programmers are starting to realize that the stack is important and shouldn't be tampered with. And as a result, there's not as many stack bugs in actual devices now as there probably was in the 1990s, for example. The heap, however, is very complicated, and most people don't really understand it very much. So there's still a lot of bugs in this region. people have to keep track of the sizes of the chunks they're using. They have to keep track of if they can even use this chunk or not. If they have a pointer, are they able to write to it or read to it? Are they no longer able to? What is being pointed to by that? These are things that people often sort of lose track of when programming. And that is very good for exploitation developers because it means that there's a lot of avenues for us to use now. And especially in large programs, this is still very much a thing. I feel like as far as like real world bugs that you'll find on a normal basis, I feel like that's probably a majority of them will be stuff that involves either heap or type confusion. Also, most programs do use the heap in some way or another, whether you know it or not. If you're using C or C++, if you make a new object or anything new, like a char array or whatever, it's going to be allocated onto the heap. Just it'll kind of happen in the back end beyond what you can actually see. Um, yeah, like I said, structs or objects are often created on the heap by stuff like this. Anything in C++ actually is pretty much done on the heap. Anytime you make strings or vectors or stuff, you'll usually just do standard string whatever equals new string, and that'll put it on the heap. And from that point forward, you have this other very volatile memory region that you have to be very careful with. And like I said, programmers are not often that careful with it as they should be. The other thing is that a lot of libraries use the heap in the back end. OpenSSL uses the heap to do a lot of its operations, and it has a bunch of file pointers and things like that. I did a recent CTF competition where there was OpenSSL objects on the heap, and those were able to be corrupted and led to code execution, which is very interesting. Also, GIMP is used on the heap. Anything that stores large strings and stuff like that often uses the heap in the back end to store the data that's pointing to. Pretty much any library, if you don't know what it's doing, it's probably using the heap in some way or another. So a lot of times you need to be careful with objects or anything that involves these libraries because you want to understand which memory you're using and if it's safe or not. Okay, so now I'm going to sort of go into a little bit of the actual bugs that you would find in the heap, like why, like what would actually happen that would lead you to be able to do a heap exploit. The two main things that you will see a lot are use after freeze and heap overflows. A use after free is basically what the name implies. Let's say you have a chunk on the heap, some memory that you allocate, and then you free it. If you still have a pointer to that memory, and under no circumstances should you just reuse that pointer. You no longer have access to the memory that I freed, and you shouldn't be touching it because there's other things that could be happening there at this time. Unless you're developing an exploit, in which case you should definitely use it. So what would actually be at this pointer? There could be the heap bins, which are basically the ways that the heap stores free chunks and optimally uses them again when necessary. There could also be other chunks that have been allocated since then. These chunks could be structures. These chunks could be different data like char arrays. It could be function pointers for all we know. It could be something else that we like a programmer wouldn't want you to just be treating as a char array, for example, if that was what was initially on the heap. Another type of use after free that I didn't really mention here is a double free, which means that you can free it and then you can free it again. And you can't necessarily use it in a better way. You can't necessarily read or write to it, but you can still free it again. And while that might seem like, oh, if it's already free, it'll just notice and not do anything. That's not actually the case. It'll do a lot, actually. So that is something else that you want to keep in mind. Okay, question in the chat. Does heap exploitation affect programs written in Rust or Go as well, or is it just C or C++? It definitely does affect Rust for sure. Go has a weird, it has two different heaps. It has like a C heap that's used for C Go, and then it has its own Rust heap, its own Go heap that's used for actual Go objects. And that one uses garbage allocation, some other weird things. I'm sure there's exploits that could be written for the actual Go heap, but it functions a lot different than the one I'll be describing. But if it uses cgo and you call something like c.malloc and c.free, it would still be very similar to everything here. Rust also functions on the heap. Theoretically, it's supposed to be memory safe, but a lot of times it's not. You can use unsafe if you have something like a vector maybe, and then that should be stored on the heap probably in a lot of cases. Um, Additionally, Rust has a lot of end days that are reported where people are like, oh, there's actually something wrong, and you can actually access stuff outside of bounds of maybe a vector or a map or something like that. So these are also things that heap exploitation would use because of that. Pretty much any language has a heap, actually. Any language needs some sort of memory to be stored dynamically, and as a result, it's going to have a heap to do that. So yeah, those ones definitely could have heap exploitation as well. If they're running on Linux, it would use the heap I'm talking about. If it's running on Mac or Windows, it would use a different one, but the concepts are kind of similar. Okay, yeah. So the other type of heap exploit, or heap bug, I guess a bug is a little different than an exploit, would be the heap overflow. So what the heap overflow is that you allocate maybe hex 40 chars or hex 40 bytes, I guess, and then you can actually work with more than that. And that's a problem because when you're accessing out of bounds on the heap, it's not like it creates a massive memory region for you that's infinite, and then it'll let you deal with that memory region for whatever it has to do. It'll actually just have other stuff probably adjacent to it. So if you have anything adjacent to your chunk and you have an overflow, you can be actually messing with that data instead. So if you allocate a chunk of size n, and you're a programmer, you should not use any more than that. You shouldn't read more than that and write more than that. And if you are making like an array of size n, you shouldn't access the nth element because that is actually one out of bounds. And that's a massive bug that a lot of people do have in their code. And as a result, there's a lot of interesting exploits for that. Like I said here also, the bins and headers, the bins and chunks also have headers that involve size and previous size and some other things we'll go into, as well as pointers to other bins that are freed. So it's very risky to allow somebody to just overflow the chunk that they created. You could also underflow if you wanted to, if you had the functionality to. If you could underflow, you could reach chunks before it in memory, for example. It's still one contiguous heap region with various stuff happening on whatever side of it. So that's also an issue. Okay, so why would a use after free be important? This is a quick little run through I'm going to give about this. Okay, so now let's think about some buffers. I'm just going to assume that each of these are character arrays in the heap. So let's say first you allocated a character array of size hex 100, and then you allocated a struct that has a function pointer. That could be a C++ object, often has function pointers in it. If you can overflow chunk 1, and due to the way that you groom the heap, you know that chunk 2 is going to be right next to it in memory, you could definitely overflow it to the function pointer if you had some infinite out of bounds, for example. And if you did this, you could treat the function pointer as a character array, which means you can just read and write bytes from it. And that would be very risky because if you can write bytes to a function pointer, you can call anywhere in memory. And that is basically the win-all condition for any sort of exploit, is trying to call your own addresses of your choice. Because then you could call something like system, bin sh, you could call a one gadget, you could call anything to pivot into a ROP chain, for example. These are very risky scenarios. Another scenario here, let's say you have chunk 1 that's a character array of size hex 100, and let's say you free that. And then let's say you allocate another chunk that is the same size, that is the struct with a function pointer inside of it. There is a very good chance, and if you know how the heap works and what bins and stuff are already there, you can know for sure if it will or not overlap with chunk 1. In which case, chunk 1 and chunk 2, the actual pointers to them, would be the exact same value, which is very dangerous because you are treating chunk 1 as a character array. You can read and write bytes, like I was saying before. So in that case, you could also just read and write bytes to the structure that has the function pointer. You could overwrite the function pointer to system and just call whatever function you want, for example. You don't necessarily have an overflow, but in a use after free scenario, it doesn't really matter because you're still accessing data that is being treated as another struct. It's a sort of type confusion bug. And that is very, very common, especially in massive programs, to accidentally leave use after freeze, because when you free a chunk, you don't know what else you have that references it. It might be referenced in a vector. It might be referenced in some other global variable. It could have been passed in a function, and it could have been modified in some way. There's a lot of things that could happen that could lead to a use after freeze. Okay, so leaks. Why would you need leaks? And this is sort of more abstract, because like this applies to any sort of exploit you create. But just in case someone's new to binary exploitation, why would you actually need something like a memory leak? The way that memory works in Linux is that it's mapped into different sections. So when you load a ELF file, for example, the whole binary will map somewhere in memory. If there is 64-bit NoPy, it'll probably be mapped to like hex 40,000 or something like that. And then it'll have a text segment, and that'll have the instructions. Then it'll have data and BSS, which have initialized and uninitialized global variables in them. And then there's also a region for the heap in memory, and a region for libc, which has all of the main C functions. If you include like standard lib or something like that, all of those are libc functions. And then it also has a stack, which is used for the actual function calls. Quick question. Okay, in the character array instruct with function pointer example, could you seed the character array with specific data so that once the struct is created in the same block, it has the attributes you want, assuming calloc isn't used? Yes, you could. That is also another issue with uninitialized variables. If somebody initializes a structure and doesn't actually initialize the data in it to zeros, the data on the heap should still remain. The first two keywords are very volatile because of the fact that those are probably going to be used for pointers to other bins and things when it's freed. But for example, if the function pointer is at offset hex 40 into some massive chunk, and you have your own fake function pointer there, and then for some reason, when the struct is created, it doesn't actually set the function pointer yet. If you can still call it before it's technically set, it'll have your data there. So even if you don't have a use after free, that would definitely be another situation which you could definitely exploit it. Yeah, that's a very good point too. Yeah, a lot of times you do have uninitialized variables in the heap. Okay, so yeah, the stack region is the last one that's like used for function calls. Basically, whenever you call a function, you recursively go up. You just create more stack space for yourself. Stores local variables, stores your return address, base pointer, other things like that. So it just is a bunch of little frames of local variables, basically. So the problem is with memory regions in the modern world, since I was alive, probably, is like, maybe not. It's since like 2005, I guess, maybe. There's something called ASLR, which is used to randomly map stuff into the address space. So for example, if the heap is mapped at address hex 100, which is very unrealistic, it's going to be some large number, but if it's mapped at like some number hex 100 one time and you run the program again, it could be mapped at hex 300, it could be mapped at hex 1000. You do not know. So the problem is you kind of need to gain some introspection on where things are in address space by getting leaks. So here's an interesting thing about like libc, and this also applies for heap and stack and other things a lot of times, not stack as much. So in things like libc, the offsets into the region are always the same, but the base is different. It moves around. So for example, here, if it's at 7 FFF and a bunch of zeros, and then system is at offset 1 into it somehow, if that's where the address of the system function is, and now it's based at this 7FF1, where do you think system would be? You can type it out if you want, but it's a massive number. You can kind of just guess a little. You can take away all the zeros. I don't care. If anyone wants to guess that in the chat. Yeah, Mateo's right. So yeah, the base will actually be the same offset from system. So it'll still be the same number added to the base of libc. Same applies for the heap if it has the exact same operations performed on it beforehand. Same applies for the binary if something like PIE is enabled. which is just position independent execution. It basically means that even the binary itself could be anywhere. You don't know any addresses when it starts. So this is why leaks are very important in developing an exploit. You need to know what you're actually going to be attacking if you are doing an overflow. If you overflow a function pointer, what are you going to call? If you're going to call system, you got to know where libc is. So that's why leaks are important to get, especially for heap exploits. So there's a GDB, which is the GNU debugger. I don't know. I think that's what it stands for. It has a bunch of wrappers, and VMMap is used in basically every wrapper you can put on GDB. And what it does is it'll actually show you where stuff is in memory. You can see here that pi is not enabled because this is just the base address of the elf up here. The elf is called realloc. This is from a pwnable TW challenge, but I didn't actually show anything like relating to a solution at all, so I think that's probably fine. I just had this running at the time. So you can see that it's based at hex 400,000, and it goes up to hex 404,000. And then you can see that libc, some massive numbers like 7F8, OBC, 30E, 000. And it has these sections as well. This is the text section. It's readable and executable. Here is a read-write section. That means that it's probably the variables that could be changed at runtime. And then there's also LD, and then stack, and then some other stuff that is important sometimes for exploiting, but I'm not really going to be going into these at all. These are just other sections. But what really matters is the fact that if you know any libc address in here, and you know it's offset to the base, you can find anything else in libc here. If you knew anywhere in heap, you'd know this base address if you know that the heap normally is based this far away from your chunk, for example. So these are things you also want to keep in mind when developing an exploit. Okay, so now another thing with the struct scenario, like I was talking about before, let's say that we have a win function in our binary. Let's say our win function was literally just system bin sh. I don't know why that would be in any binary, but let's say it was there. Maybe it's like an authenticated login or something like that. So this is stored inside of a struct called the print struct info. And this print struct info, okay, wait, I kind of worded this really badly. Yeah, so let's say there's a structure that's an object, and let's say this structure has a way to print information about it that's stored inside of the structure itself. So like a C++ object has functions stored inside of a V table or inside of the object itself, maybe. So in this situation, you have a struct, and in normal runtime scenarios, some offset into the struct will be treated as a function pointer. So let's say this is like the same scenario as before. You have a UAF or an overflow, but basically you can treat the struct's print struct info function pointer as a character array. You can change it. So if pi isn't enabled, the position and execution, the binary is always going to be based at the same region. And that would probably be this 400,000 if it's x64, for example. So you don't need a leak. The win function is going to be in the same place in memory every time you run it. You can just override it with that, and then you're set. However, let's say that position independent execution is enabled, in which case the binary is not based in the same region each time you run it. This might seem like a problem because you're like, oh, it could be at 7FF something, or probably not. It's going to be like at 55230 or something crazy like that. But you don't know where it is. And if you just put another thing, it'll just fault or segmentation fault because it's calling unmapped memory. But that's not really a problem in this case because in my scenario that I created, you can read and write from the character array. So what you could do is you could print out the function pointer as characters, in which case you will have the address of print struct info in memory. And you will have the actual virtual address of it. You won't have the offset. But the offset is always going to be the same, like I was saying before. So you can subtract that offset from your leak. Now you have the base of the binary. You can add the offset of win into the binary to this. Now you have the win function. Now you could write that into memory there, and you're good. You can call your own functions if you want to. Is this actually like a realistic thing to have structs like this? Well, yeah, it is. C++ is object oriented, which is good and bad. So a lot of the objects have V tables in them. What a V table is I guess VF table is also what people call it sometimes. It's a pointer to a table of function pointers. So what it is basically a bunch of function pointers in memory. One of them might be printing. One of them might be some attribute of the object, a getter, setter, stuff like that. Um, C plus objects often have pointers to character arrays as well. First one that comes to mind is strings. String object is basically a size and then a pointer, and then hex 10 bytes of data if it's small enough. If not, it'll malloc another struct. But what matters is that there's a pointer to a character array inside of this. There's also objects with pointers to other objects that you could be able to maybe overflow or affect and use after free. STL, standard library for C++, there's a lot of these. Vectors could store object pointers, maps could store object pointers. These are often used on the heap as well, especially if you use new, it's going to be on the heap. So what happens if you can overflow or use after free character array into a C++ string, for example? In this case, you can control the size and you control the backing data pointer, which points to the actual characters. This is not really a function pointer. So at first glance, it might not seem like you have an ultimate win, but you basically do in a lot of cases, because you can put the backing data pointer wherever you want. You can overwrite that to any pointer in memory, and then you can read or write from that. So you have an arbitrary read-write in memory. Again, if you have a leak or if there's no pi, you could point that in something like the global offset table, or if you have a leak for libc, there's other things you could do with that I'll go into. But basically, being able to write anywhere in memory is a very, very good primitive. And being able to read anywhere from memory is also a very good primitive, because you can kind of create a maze through all of the memory segments to where you're trying to go. For example, you could read the global offset table from the actual binary, and then libc. Then you can go into libc and write in there. So it's a very, very strong primitive. So yeah, let's say that pi is disabled. You can write into the global offset table like I mentioned before, which is great. So it stands for global offset table. It's GOT. So it's a bunch of pointers to libc functions that your binary will call. So if it's not static, which would make your binary massive, then the global offset table will be pointing to stuff like printf or puts or read or whatever other libc functions you call as you do this. So for example, if you call printf, what it will do is it'll find the address that's stored in printf at global offset table, and then it will call this address with the arguments it's given. So if you read the global offset table, you got a libc leak, then you can also overwrite any arbitrary function call. Because if you have a libc leak, then you know where all the functions for libc are. Like I was saying, you could just fix the address, subtract the offset to get the base, and then add the offset of whatever function you want. So what happens if you can't write into this global offset table? Maybe you don't have a pi, maybe pi is enabled, you don't have a leak. Maybe it's a full rel row, which is basically just saying that you can't write into the global offset table. Basically, it's some modern mitigation technique. There's this very interesting thing that I don't know why it exists. I assume it's for debugging purposes. If anyone knows, you could definitely tell me. But it's these hook functions that are in libc. There's one called malloc hook, there's one called free hook, and there's also one called realloc hook. And these hooks are called when these respective functions are called. So for example, I'm assuming it's for debugging purposes, but I've never heard anyone use these in real life outside of exploitation. Let's say you wanted to know what data you are freeing before you freed it. You could overwrite it with printf and then just print argument 1, because the arguments passed to the hook are the same as the arguments passed to the respective function here, like malloc, free, or realloc. So this is a very, very good thing for us to attack, because, for example, wait, let me see. Couldn't you just LD preload a library defining those functions and then go nuts? Well, if you had LD preload functionality, you would generally already be on their server to do that. So for example, a lot of these situations are like something's running on a network on a socket, and you're trying to use this to get like a footing into their machine to read files or change files or whatever else. So in this situation, you couldn't really LD preload it because you can't start it remotely. If you could, you'd start bin.sh remotely instead, probably. The other thing with the LD preloading is, yeah, if you had the LD preload, you could also load a library of the constructor to execute anything you want. Yeah, that is also true. The other situation in which you'd exploit something would be to gain more privileges, for example. So if there's yeah, that's it. It can't be used with SUID binaries. That's the big one. In modern libc versions, and I think that it wasn't true in old ones, which was a problem, but in anything that you might touch since like 2006 probably, if you have a binary that could give you more privileges than you have, or it can set user IDs, you can't actually LD preload it. The Linux kernel will not let you. It'll fail. So as a result, you can't really just do that because, yeah, if like as you were saying, if you could just LD preload libc start main, which is always called, with system bin.sh, and then you'd be set. But that's sadly not always the case. I mean, that's very, very smart though to think about that, because in the old times people did do that. That was a very common attack, was just LD preloading your own stuff into binaries and then going from there. But sadly, that doesn't really work anymore. We gotta adapt, sadly. But yeah, I hope that answers your question. Okay, so with the example with the hooks, let's say that we had arbitrary read write inside of libc, and we wanted to call system bin.sh because that's always the goal. Then what you could do is you could overwrite the free hook with system, because you could read. Well, if you had libc leak, you know, if you knew where the hook was, you would have to have a libc leak, and if you have a libc leak, then you also know where system is because of the thing that I was talking about. So you could overwrite the free hook with system. What will the argument be? The argument will be the pointer to the chunk that you're actually freeing. You could put bin.sh in your chunk, it's a character array, and then null terminate it, and then bam, you have system bin.sh, and you've won. So most actual heap attacks, something like that is very common, especially in like a toy CTF scenario, is trying to overwrite these hooks and then using those to get more code execution. Okay, what else could you actually do? If there's specific, oh yeah, magic gadget. I think that's what it used to be called. I think it was also called bespoke gadget or something else weird. I always call them one gadgets because this guy, David942J from HitCon, he made this tool called One Gadget. And what it does is it finds specific ROP gadgets in libc that if you call them with a certain constraint satisfied, you will get execve bin.sh, which is system bin.sh basically, except it has more arguments. And they all have just little constraints. So if you notice that your stack is mostly null bytes, and you notice that at hex 40 offset into your stack is null bytes, then if you call this function offset inside of your libc leak, or I guess libc base that you calculate, and then oh my god, Adobe, and then do whatever, then you'll basically be set. It'll call execve bin.sh, argv will be a null byte, which is what it's supposed to be, and then environment will be environ, which is also fine. So you'll have a shell right away without any arguments. You don't need to control RDI, RSI, RDX, anything. Yeah, so this is like very, very important. A lot of times when you overwrite something like the malloc hook or free hook, you don't really control the chunk. Or for example, if it's the malloc hook, you can't really malloc a size of an address to bin.sh in most cases. A lot of programs will have checks and be like, hey, you're trying to allocate something that's well over hex 200,000. Yeah, no, that's not going to happen. But if you have one gadgets, then you have these other little constraints that you might notice through a debugger. Hey, wait, RCX is null. This will work. And then you are set. Okay, so we have use after freeze and overflows. We can just affect structs and stuff. So that's it. That's all of heap exploitation. Well, no, not really, because a lot of times you don't really have the information on the heap that you really need to. For example, what if you don't actually have any character array pointers inside of heap chunks? Like the heap chunk itself might be a character array, but you don't have a pointer inside of there. Then you can't really get an easy read-write by just overriding this pointer. What if there's no function pointers? Well, then you're not going to be calling a function right away by overriding it with your overflow or use after free. What if you don't actually have any libc or elf pointers stored in these structs? How are we going to get these? This is also a problem. But that's okay, because that is what the majority of heap exploitation is these weird scenarios in which you actually abuse the way that the heap works and that the bins work and that all of this stuff works together in order to actually get these primitives back. So you don't always need structs and easy string overflows or function pointers to win. There's definitely other ways to get your shell. You don't have to worry about that. Okay, so now the most important thing to doing that is actually understanding how the heap works. The heap is kind of complicated. I don't think anyone really understands it all the way. I don't think I understand it all the way, but I think I understand it enough. And I think that there's a few things that you'd probably want to know before seeing how the attacks work. The main thing is that it's not magical. It's not like the operating system like waves a wand and then bam, we have this memory you can use. It's perfect. There's some sort of an algorithm that happens inside of glibc, and this helps you choose which chunk you're going to be given based on your size and based on what's freed already, based on anything that might be already on the heap, stuff like that. And the other thing is that when you free a chunk, it doesn't just like disappear. It goes into some list, and these lists are used, whether it's singly or doubly linked, I'll go into later, so that later on, if you allocate something that's the same size, it can repurpose that memory for you. So the whole goal of the heap is to not exhaust memory. If you just free the memory and then you can't use it for any other chunks that you create, there's not really any purpose in freeing it. So that's the whole point, is that it's still going to be somehow stored and sorted in a way and then given back to you eventually. So these aren't just empty data. They don't just like zero it out, for example. Like I said before, they don't actually zero it at all. But what might happen is there might be pointers to other chunks in these data, and these pointers to other chunks. I have an issue. Okay, so there might be pointers to other chunks inside of these freed bins, and there might also be pointers to glibc, where the actual heap base and all that stuff is actually stored itself. So if you can't abuse other structs in the heap, that's not really a problem, because you could still, in a lot of cases, abuse these bin pointers or libc pointers or other things to get what you need. So a little bit of a data structures review. I saw some people talk about DSA in the chat earlier. I assume that was data structures. There's two main types of linked lists that are used in the heap. And something that might surprise people, the heap isn't the same as the heap you learn about in data structures. You're not going to be storing stuff as a tree and then recursively like fetching tree items. Like it's not like that at all. So there's the singly linked lists and doubly linked lists. Singly linked list, they're both kind of self-explanatory by the name, but basically it's first a head, and this points to the first element, then the second element, and that second points to the third points to the fourth, and so on. Eventually it's going to end at a null byte. It has to know when to end. So the other example would be a doubly linked list, in which case the chunks point forward and backwards. They have a next pointer and a previous pointer. In this case here, the next pointer, the final one, ends at null byte. At a lot of doubly linked lists, this actually loops back to the head somehow. So these are like the main ways that memory chunks are like sort of linked together, is through singly or doubly linked. And that is used in the actual glibc heap as well. So what are the bins? Luckily, there's only really 4. There's like some other weird finicky stuff, but these are like the main bins. So the first one's the fast bins. These are used for smaller data chunks. They're only up to hex 80 bytes large in x64. And it's a singly linked list. You don't have to do any sort of weird stuff where you point the previous and back to each other when you remove an element. It basically just rewrites the head to the pointer that this one has and then gives you that memory. And because of that, it's like the fastest acting one. It just basically dereferences the pointer, moves the pointer, and then it returns to your thing. So this one is very fast. That's why it's called fast bin. And that's why it's used for smaller bins as well. If you're working with chunks, a lot of times they're going to be small chunks. You might have some struct that's like hex 20 bytes large. You might have a lot of those actually. So they need to be very optimal. The whole goal with making libc was to make it optimal, not just secure, as is often seen. The other types are small bins. Those go up to hex 400, I believe. I might be wrong. I mean, also when I'm saying this, I'm meaning without the header size. It does some other things, but like if you malloc hex 400, that should be a small bin size in x64. Um, a lot of times you can use them for all the way down to fast bin sizes. There are small bin chunks that are used for fast bins that are less than like hex 80 even. You might have a small bin of size hex 20 somehow. And this happens in some weird ways that I describe later, but they have the bins for all of those. Um, there's large bins, which, as it might make sense, are larger than hex 400. This is also a doubly linked list. And this one has a very interesting caveat, and that it's not just one size that is inside of the bin. The bins have much more ranges because you get incrementally larger. You don't want to have a bin for hex 408, 4010, 418, all the way up to who knows what. That would be very inefficient. So each one has a doubly linked list, and each of these chunks also has a list based on the sizes inside of that specific large bin as well. So that's a very interesting part that I'm going to go into a lot of detail later. And then there's also the unsorted bin, which is sort of a temporary location. When you free chunks, they don't always go straight to small or large bins, especially if they might be allocated again right away. So when you free something that's not a small bin, it'll end up in the unsorted bin. And then later on, through whatever mallocs happen or freeze or stuff like that, eventually they'll get sorted into small bins or large bins as needed. And the unsorted bin is also a doubly linked list like the other ones. The only singly linked list is the fast bin. And there's also something called the top chunk. The top bin, also called the forest. If you see someone talk about the forest on the heap, this is what they usually mean, is the rest of the heap that's not actually allocated yet. When you create the heap in memory, it's like some massive nmapped region, and the rest of it that's not been used yet doesn't have to be stored as a massive large bin, for example. It's stored as something called the forest. And when you make a chunk that is like not actually going to be served by a fast bin or a small bin or large bin, for example, the only thing really left is to pull out of the top bin. Let me see. Isn't the top chunk usually called the wilderness? Oh, yeah, it's called the wilderness. I messed that one up. I mean, I always know it from the House of Forest, so I always call it the forest. But yeah, no, it's called the wilderness. That's kind of close to forest. I assume people also probably make the same mistake I do. But yeah, it's called the wilderness. My bad. Thanks for calling me out on that too, though. Like, if I make any mistakes, please tell me because I want to make sure I can go back and fix it later. Yeah. So what happens if you have no bins that are ready to serve you whatever chunk you need? It'll basically just pull it out of the top chunk. It'll be like, oh, the next space in memory at the header of the top chunk will give this to you, and then we'll move the header of the top chunk down enough that you have this new space for you, and it slowly chips away at it. When you free certain chunks that are at the top or that are like adjacent to the top chunk, a lot of times they will coalesce with it because it just wants to make the top chunk as big as possible. If you can combine them and it's not a fast bin in most cases, I believe, then it will. I think fast bins also can coalesce with the top, actually. I'm thinking T-cache later on. So the other thing is that the top chunk is basically just a really large free bin minus the pointers. So it has a size and a header and stuff in a previous and use bit, like I'll go into later. So it's basically treated like a massive bin that you can just pull parts out of. Once the size is too small, once you've used up the whole heap that you have somehow, then it'll nmap another region or extend the nmap region in a way so that more heap can actually be used. And this is called sysmalloc, and I'll go into this later as well. So the whole concept of the top chunk has a few weird attacks just because there's this one size and then a bunch of data you can use, and sometimes you can do weird things with that, and sometimes those get patched, sadly, but there's a few cool attacks that involve the top chunk that I'll go into. Okay, so now the newest addition, I lied when I said there's 4, there's actually 5, is something called the T-cache. And the T-cache is the thread-specific cache. Basically, in a lot of like single-threaded programs, it's just another bin. It's a singly linked list of chunks, and the size is stored as well, the size of the linked list. So if you have one element in a T cache of size hex 20, you'll have the pointer somewhere, and you'll also have a number 1 somewhere saying, hey, this hex 20 chunk has just one thing in it. And all this information is stored in the per thread struct. And this is actually the first chunk stored in the heap arena that's created. Basically, like if you make a new thread, there'll be a new mmapped heap for you. And this will also have a tcache per thread struct that's different than the other ones. So like as I show here, the per thread struct is down here. It has a bunch of character. It has a character array of the different counts. In different versions, the short versus a character though. And then it also has a bunch of pointers to the Tcache entries after that. So these are also interesting because these are stored on the heap, unlike the other ones, which the heads are stored inside of libc actually. So that makes this whole thing a little bit different than fastspin or anything else. And there's other reasons different too that I'm going to go into when we get to the modern era. Okay, so where are the heads of these linked lists? Like they can't just come out of nowhere. They have to start at somewhere where libc can know to recognize them, follow them, and then eventually reach the chunks that they're trying to serve back to us. So there's this struct called the malloc state. There's a main one of these is called main arena, and that's the first malloc state that's actually created and stored inside libc. And that's generally what we'll use if we have like a single thread, for example, is the main arena. So what's interesting about this is that this struct has the heads of the fast bins, it has the heads of unsorted, and then the small bins, and then the large bins as well. And for these, it has the pointer that's going to go out to all the different chunks, like the linked list would be imagined. There's a pointer to the top chunk as well. There's a bitmap that I don't really know how it's used. I haven't seen any attacks or anything involving it. But then also has a linked list to the other arenas as well. So if you have a new thread, which has like a secondary arena, the main arena will point to that. That one will also point back. So that's basically all stored inside of libc itself. So this is what the malloc state looks like in the source code. I also have this in Wobok. I got all mine from there. So yeah, as you can see here, there's the minimum fast bin pointers, and this is an array of fast spins y for the number of fast spins. Then there's a chunk pointer to the top, chunk pointer to the remainder if there's been a split, and then there's all of these bins as well right here. So this is, and then the bitmap for the bins, and then the linked list with the other ones. A lot of stuff doesn't really matter too much, and system mem is also I'll reference that a little later, but basically it's a massive struct inside of libc. I'll just usually call it main arena because in most cases we're going to be talking about singly threaded heap exploits. So this is basically how it's all stored inside of libc. So is that everything? There's a little more that's kind of important. The chunks have headers. That's something that you might want to keep in mind. Usually if it's like a 64-bit heap, there will be 2 keywords that are treated as the header. And one of them will have the size of the chunk, and then the other one will have the previous size if the other chunk before it is free, so that I can kind of have a track of, is there memory that's before me that I can use, or is there not? Is that already in use? There's also flag bits. The sizes has to be basically something like hex 81, hex 91, hex 401. It has to be, or basically it can't be just like a random number because the bottom bits are used for other stuff. The first bit is if the previous in use. So if it's like number like hex 21, that means whatever chunk is right before that in memory is being currently used and is not free and isn't something you can like coalesce with or have the libc sort in some way. There's a is mmapped flag, which is kind of interesting. There's a few exploits that involve that, but they're kind of confusing. And then there's another one for non-main arena, which is basically like, hey, this chunk wasn't actually created by the main arena. It's made by some other thread, and it has some other arena. And there's a very cool attack that has been recently fixed that I'm going to be talking about that involves non-main arena. There's a few other quirks too. I'll go into them as I need to, but one big thing that you might want to keep in mind is if you make a chunk that can't really fit in the heap or is just too large to make sense to put in the heap, it'll just call mmap and return you that instead. And that'll have the ismap bit set here actually, but it won't be on the heap. It'll be somewhere else in memory. It'll be its own mmap region. Um, there's a global variable in libc called global max fast. That'll store the maximum fast bin size in like x64 default. It'll be hex 80, which means if it's less than hex 80, you can try to make it a fast bin. If it's greater than that, don't even bother. Our fast bin array isn't big enough. It won't work. There's a struct called the malloc par struct. The main one is called mp underscore. That holds some other information that's kind of cool. I'm not going to go into most of it too much. It involves tcache and a few other specific settings. And then the other thing you want to keep in mind that you can call in C is something called mallopt. And basically, you can use this to set some parameters. You can use it to set max fast. You can set mmap threshold, a few other things. So if you're designing a program in C and you want everything to be really fast, then you can make the max fast ones very large, for example, just things like that. Okay, so that's all of that I'm going to go into now for actually how the heap works. Now I'll be able to actually get into the cool stuff about how to get from heap to actually like exploiting it, which is what I think is the interesting part. Okay, so how did I learn this, first of all, before I go into the different attacks? When I started, I basically just learned the houses. I used how to heap a lot. And I referenced how to heap a lot when I made this PowerPoint too. It's a very, very great resource I recommend people look at. But basically, I just kind of went, okay, here's an attack. Here's how it works, or at least here's what I do to make it work. And then I kind of moved on. I didn't really understand why they worked a lot of times. I didn't get if they got patched, why it would matter or not, because I didn't know what actually was happening. And then there's also this paper. This is like really old, but it was like this email. I don't know, some plain text email someone has. That's basically like all of the original houses, and it's a lot of heap exploits way before 2.23 even, and it was kind of a foundation for a lot of stuff we do now, but it's very outdated. There's a frac version that's like slightly newer, but it's also very old. So the problem with how I learned was that the houses are good for kind of having these patterns that you can use in an attack. You might be like, oh, I have a free that I can overwrite. I can like an arbitrary free. That sounds like House of Spirit. And then you just copy some code from somewhere and hope it works. But the problem is that a lot of times you can't really just do that. And also glibc will update, your code won't work like it should. Stuff might be slightly different. And if you don't know how the attacks actually work, it's not going to really help you much. So the problem is that you really have to understand how they work. I think understanding the different primitives means so much more than just memorizing attacks, because I feel like you always look up an attack and see how it works and be like, that was cool. But if you want to actually ever implement something like that, it's very, very useful to understand it, because if you don't, and it doesn't work on the first try, you're kind of out of luck. And that was an issue I ran into a lot starting off. So that's why I'm trying to go into a lot of the code and stuff. So when I'm explaining attacks, I'm going to try to go from the easiest ones to the hardest ones. I'm going to start with the attacks where it's like, if you can do something like this, please do. This is the best way to do it. And then I'm going to get to the harder ones as well. But I won't just explain like the code. I'm not going to give you code that you can copy and paste. I'm going to kind of go into how it actually works and like how you can visualize it in memory and how you could sort of implement something like this in other attacks or as a primitive for whatever else. So when you're like doing this, try to like just see how the primitives work. I think memorization is like the main mistake a lot of people make with heap exploits. That's an issue I made and a lot of people I know. It's important to understand how it works more than anything else, so you can adapt and find new attacks. And I searched adapt on Google Images, and this came up, and I was like, this is perfect. This is how I feel. Okay, so for all of the scenarios that I'm going to talk about here, I want you to assume that we have each chunk as a character array. That's the easiest way to do this. And you have some normal functions. You can create an array of a certain size. You can edit it, possibly bounded with the size that you're supposed to have. You can view the array, for example, or offsets into it, and you can delete it, which is just freeing. These are pretty standard. We can maybe say that everything's indexed too. It's not like you can just start at the beginning or make strings. So this is kind of what CTF challenges do a lot of time. A lot of times you have a 4-function heap is like the meme. There's so many of them. And it's very useful for understanding how attacks work. You have the most control over it. Everything makes sense. You can control anywhere because of the character array inside of your chunk, which is not always the case with stuff like structs. But for the purpose of understanding the primitives, I think that's probably the best way to do it. Also, at least for now, I'm going to be going over attacks before 2.26. So this is before Tcache was actually created. Since then, there's been other stuff happening, but I'll go into that later on. But for now, take yourself back to Ubuntu 20, Ubuntu 16, you know, back when I was like a freshman and learning attacks and stuff like that. And I'll go through it then because it was a little more easy to understand. And then as stuff changed from then, I'll show how attacks adapted and how people created new ones sort of as time progressed. I think that's a very interesting way to learn about stuff like that. So the main one, the default attack, at least for 2.23, is called the fast spin attack. This is like the most common one. And as I mentioned before, oh man, I messed it up. Okay, fast spins are a singly linked list. I meant to put singly here. It's the only singly linked list, and I didn't put the word singly. I should have edited this way more. So yeah, fast spins are a singly linked list, not doubly. So basically, there's just a bunch of forward pointers going to each of the other chunks. You'll have a fast spin head, and for example, if it's size hex 40, it'll point to a free chunk of size hex 40, then another free chunk of hex 40, then that one will have a pointer to another chunk of hex 40, all the way until it hits a null pointer. And when it's a null pointer, it means there's no chunks past this. This is the last chunk in this fast spin. So there's a very obvious attack that becomes apparent from this, is that if you can overwrite the first keyword, which is the forward pointer, you can basically put your own chunk in there. It'll start following the list. It'll go from the head to a chunk, and then it'll hit this one that you overwrote, for example, and then it'll be like, oh, this next one's at hex 41414141, for example. If you just put A's there, and then it'll try to allocate a chunk there as well. So that is a super useful primitive because you can just basically insert your own fake chunk into a list and then get it given to you by the heap for character array access, reading, writing, viewing, whatever you want. So the problem is that there is a little check that the size is correct. Basically, if you're like, hey, I'm going to insert a fake chunk in here, and then the bytes before it are like a libc pointer, like 7F80, blah, blah, blah. It'll be like, hey, this is not hex 40. This isn't the right size for this fast spin that we're serving you from, and it'll just like fail. So the main issue is that when you're doing this, you need to make sure that you have something that's about the same size as the list you are inserting yourself into. So that is pretty important to keep in mind because otherwise you'll have some weird assert errors and stuff like that. And also, if you just point it anywhere in memory that's not mmapped, it's just going to segfault. Like, it will no longer succeed at all. It'll be like, hey, hex 4141 is not actually an address, and it'll just say no. So here I put a little bit of an example code for a fast spin attack, for example. So we malloc 2 chunks of size hex 40, and then we free the first chunk, and then we mem copy a bunch of like 8 A's into this chunk. I created chunk 2 here because I didn't want the first chunk to coalesce into the wilderness. So what we have now, if we free the first chunk, is we have fast spin for size hex 40 points into chunk 1. And chunk 1, as it's the only free chunk, will not point at anything. There's no other free chunks. But what we can do is if we mem copy A's into this free chunk because of use after free, for example, then when we allocate chunk 3, it'll give us back chunk 1. It'll be like, okay, here's the first chunk, move the head up to whatever value is there. And then when we allocate chunk 4, it will give us a chunk at hex 414141 and so on. And that's not valid memory, and it will not like that. So what'll happen if we do that? Oops. 6AV in GDB. I'm using PETA. I don't know why. So it crashed. Why did it crash? Okay, let's look at what's happening at the instruction that crashed. Move R8, the keyword pointed to by RCX plus hex 10. Okay, what's RCX? All 4 ones, hex 4 and 4 and 4, and like I said. So what that means is that it's doing something and setting up a chunk at this address. And as I said, this address is not real. That's not actually MF memory, but we can put that into the fast bin list because of our use after free. So that is what you can do with something like that. So when you have a single free fast bin, there's no other bin that it points to. It'll be a null byte there. But if you have multiple free chunks of the same size that are going into the fast bin, for example, they'll point to each other as a linked list. So what you can do is you can get a heap leak. You'll be able to use that if you have a use after free. Because, of example, let's say you have 2 chunks and then padding, and you free one, the head of the fast bin list will point to that chunk. Now, if you free another one, what will happen is the head will point to your new freed one, which will point to the first freed one, which will point to null. So if you have a use after free and you can print the information inside of the most recently freed one, you'll realize that it's random ugly looking data, and that ugly looking data is a heap pointer. So you should keep in mind, malloc doesn't necessarily clear the chunk as well. So sometimes if you can malloc and print before it's even initialized, you can see this without even having a use after free, for example. That's something else you want to keep in mind as well. But calloc is not as great. So here's an example of getting a heap leak. I create 3 chunks, like I said, free the first one, free the second one. And then, like I said, the first keyword of the second one, I did some ugly casting here, will be the leak that we get, and that should be a heap pointer. And when I ran this and compiled it, you can see all of these things each time I run it. Each of these is the base of the heap for that runtime. And this also shows ASLR because they're all different. But for example, when I ran this first one, this right here was the base of the heap at that for that program. This is the base for this one. And because of this, I showed that it actually is pointing to the first Tcache. First Tcache is the first thing in libc, in the heap, my bad. So that shows how you can get a leak with something like a fast bin attack. So yeah, why did I include chunk 3? One of the main issues that people have, and I had a lot when I started doing heap stuff, is that your chunk kind of just disappear. And it's always like, where did it go? But what happens is if your last chunk is freed and this chunk is next to the top bit, or the wilderness or whatever, the massive space that is ready to serve you, then it will just merge with your chunk. And that shows here. The chunk border is at the current high end. This is a libc snippet. It'll basically add the size with the top bin size, and then it'll set the top to this chunk, and then it'll check it to make sure it's good and stuff. But basically, it will just coalesce your freed bin with the rest of the top, and you can't really do it fast bin attack anymore because it's not a fast bin. It doesn't have the pointer, and it's not going to be followed. Okay, so libc leaks. The problem with fast bins is that they're not doubly linked. They won't point back into libc ever. It'll be a pointer to the next, to the next, to the next, to null byte. So the best way to get a libc leak on the heap is through another bin. All the other ones are doubly linked, so you can just free those, and then you'll have the pointers to the head of that bin. So if you have a chunk that's like hex, I don't know, 400, and you free it, and it's 2.23, of course, then this pointer, the first and second keyword pointers, and I'll go more into this when I go into the attacks for unsorted bin, but as far as leaking purposes, those will be pointers to the unsorted bin head in libc. If you had multiple, the first bin would point to libc, the second will point to the next unsorted bin, and so on until the last unsorted bin, in which case the next pointer will also point to the head again. So basically anything but a fast bin will give you a libc leak. Like I said, just allocate something bigger in a fast bin and free it. That's the easy way to do it for any other libc, for 2.23 at least. And then when you allocate on top of it, if it's not initialized, then if you print it, you'll see your libc leak. If you can't really do this because it initializes your chunks, then it's not quite as easy. But I'll go more into that later, way down the road. So, but for now, just keep in mind that because any other bin is doubly linked, at least two of them will have, or at least there will be at least two libc pointers for each bin on the heap, whether it be the final next and the first previous. Just think about like a circle. Okay, so how do we get a libc leak? Okay, so this time my first chunk is of size hex 400. My next chunk is of size 10, and I free the first one. Like I said, the default global max fast is 80 or hex 80, so that is not going to be a fast bin. That will go straight into the unsorted bin and get ready for whatever else. So now I'm going to malloc size hex 40, or whatever I want less than hex 400 really. And then the first keyword of that should be the previous pointer of the unsorted bin, which will be a libc leak. And let's see. Okay, cool. When I run it, what I get is these leaks here. And as you see, these start with 7F or 7E, and they're big, and they all end in F68. And that goes back to what I said about the offsets within libc being the same. Whatever libc version you're using, at some offset that ends in F68 will be the unsorted bin, for the one I was using at least. And even though everything else changes, that stays the same. So as you can also see, there's ASLR. They change every time, but each time I do it, I get a libc leak. So, simple fast bin attack. The one time I did it, I seg faulted, like I showed. I made 4 ones, wasn't pretty. I got some exploit, but it wasn't great. So now, where can I actually fake a fast spin inside of libc? It doesn't seem like an easy thing to do, to have just a random number that's a good looking header somewhere where you want it. But the other thing to keep in mind is that libc, like I showed here, is based at 7F or 7E or something like that. Normally 7F, I believe. So you can move it in memory. You can shift it by adding 1 to the address, and now the lowest byte will be 2F, adding 2, 3, 4, 5. And at this point, the lowest byte will be a 7F, and that is less than 80. That's a valid fast bin size. So when you see this here, here's my malloc hook that I'm trying to attack is at DD1B10. And I'm like, okay, cool. Let's see what's before this in memory. So I subtracted hex 13 and then hex 10. And here is a 7F. Oh, that is an offset of some libc pointer. You can see the rest of it on the line below it. But basically what matters is 7F will work. That's a valid chunk size for a fast bin of a certain size. So we can create a fast bin here. The interesting part is that if you want to make a fast bin of size hex 70, you really have to allocate hex 60 because of the fact that the header with the previous size and next size and all is actually hex 10 large. You could even allocate technically up to 68, but what matters is if you allocate hex 70, it's going to be serving you something at size hex 80 instead. So hex 60 is what you need. So here's some code I wrote to do a simple fast bin attack. First, I wanted a libc leak, so I did it the same way as I did before. I malloc hex 40, I made some padding, freed it, printed, bam, there's my libc leak. I had to use that for free in my scenario. Then I decided to do a fast bin attack on size hex 60. So I created hex 60. I created another chunk of size hex 10. I don't know if I really had to do that, but I didn't want it to coalesce with the wilderness if I was at the actual adjacent to the top chunk. So I did just in case. And then I freed chunk 1. So now fast bin head points to chunk 1, points to nothing. So with my libc leak, first I found the base by subtracting the offset of the unsorted bin. Then I found the malloc hook pointer by adding the offset of that. You can just find these with GDB, to be honest. I don't think there's like a really nice way to do that. And then I subtracted hex 13 and hex 10 like I did before, and there's my fake chunk. And when you create a fast bin forge chunk, you actually have to point hex 10 below where you think you should. Like, I know my data is going to start here because there's my header, but it includes the header in the pointer list. So actually, you need to point it here. So minus hex 13, hex 10. And then I set this fake chunk pointer inside of my free fastbin. So now it points to head of it, chunk 1, and then fake chunk. So I allocate 1 time to get fake chunk back, and to get chunk 1, and I allocate again of the same size to get my fake chunk, which is in libc. So now what I'm going to do is I'm going to put the keyword pointer at hex 13, which is where the malloc hook is, to be the win function. And then I'm going to malloc hex 10. And what really matters here is that when I malloc, it'll call this malloc hook, like I said before, and it'll call win, and it'll be like, hey, good job. So if this works, what matters is that I was able to actually overwrite a function pointer that's called by malloc in order to call my own functions with just a fastbin use after free. And when you run it, I get my good job. I also have the other prints because I printed the libc leak. And did I print something else? I think I printed chunk 4 address. Yeah. So the libc leak is at 7.8, and chunks 4 address is at 8 AFD, which is my fake chunk that I created. And then it says, good job. Awesome. Yeah. Have a good one, Jack. Cool. So yeah, that is a basic fastbin exploit. And if you can do it for a heap exploit, this is like peak. This is like what you want to do. It's the easiest by far. So when would you use this? Like I said, as it's singly linked and it only really checks the size, it's pretty simple. It's not the most restricting attack. If you can view, you can get leaks, like I said. If you can edit it after you're freed, you can corrupt the linked list. But you have to be able to use fastbins. And like I said, the fastbins only go up to size hex 80. There will be a lot of attack scenarios where you can only allocate above hex 80, for example. Maybe for some primitive that, or like a CTF, they might want you to do another primitive instead. In a real world example, maybe the structs that are being used are just not that small. So a lot of times you can't actually do a fastbin attack. But if you can, you really should, in my opinion. I think this is the best, the easiest one. For 2.23, there's one way easier in the future. Okay, so now, what if you don't have a use after free, but you have a double free? Could you just free the chunk into the fastbin twice and then have it point from head to the chunk to itself just repeatedly? No, and you can't really directly do that because it checks here if the top of the bin is not actually what we're trying to do. So if it checks the top of the fastbin, which is the head, and it's equal to the new chunk that we're linking into it and freeing, it'll be like, hey, you can't free this again. It's a double free bug. And then when it calls malloc print error, it aborts. It exits everything. So it's not like this is like recoverable. This is the end of the program. So you'll realize here that it only checks the first pointer of the fastbin list. It'll check old. It doesn't do a while loop or anything like that. So there's a few ways we can deal with this. Did I put the other one too? Okay. So there's a few things we could do with this. One of the ways to bypass the double free, because I said here, it only checks if we free it from the first chunk, is we could free it again. We just have to free something between it. So for example, if we had 2 chunks that are the same size, free one, free the other, free the first one again, it'll pass the check because the other one is there. But we still are in our linked list and we still have the same chunk twice. So if we allocate it and edit it, it's still going to be going through that linked list, through our chunk that we have access to. So you can still get a good use after free with the double free if we do another chunk between it. It only does it if you do it twice. The other thing is that it only checks the fastbin list. So that's something else interesting here, is that it doesn't check unsorted bin or small bin or anything. It's just, hey, is this in the fastbin list? Okay, then we can't do it. So there's another bin called the unsorted bin, like I talked about. It's like a middleman between all of the other bins and being just freed. It stores them before it decides to sort them, basically. So, how do fast bins go there? Well, thanks to the comments in libc source code, which are very nice. There's this function called malloc consolidate, which basically puts all the fast bins into the unsorted bin. It decides we're going to empty out this list and put these in the unsorted bin so that they can be put into small bins. So how is malloc consolidate actually called? So do I actually say that here? Do I? No, I don't know if I do. Okay. So basically, like I said before, with unsorted bin, it only contains like the doubly linked list of bins to sort at that time. It doesn't have, it could be all different sizes, all different who knows what. So if you have a fast bin, wait, I feel like I worded this really badly. I know how this attack works, but I worded it kind of weirdly. Okay, yeah. So if you free a fast bin and then you call a consolidate, which is created when you make a large bin, basically, if you have a bin that you create that's too big to be served by small bins or fast bins, and you make a large bin, for some reason, libc decides, okay, we don't want any more fast bins. We're gonna put all those into the unsorted bin. So what you can do though is after you create this large bin, you can also create overlapping fast bin size chunks by freeing it again, as it's inside of the large bin now instead of the fast bin. And that's kind of interesting. Inside of the unsorted bin instead. So what you could do is you could allocate it and free it, and then you could call malloc consolidate, and then you can free it again. And now you have a double free again, but you don't actually have the double check because of the fact that it's not in the fast bin, it's in the unsorted bin. And when you put something in unsorted bin, like I said, first one is going to point back to the libc head of the unsorted bin. If it's another one, it'll point to another unsorted bin. Either way, it's not pointing to itself, and that's all that matters. Okay, what if we can't actually malloc directly? What if we want to consolidate fast bins, but we don't have a way to malloc a large bin, for example? It's okay. It's not a big deal. Don't cry about it. Basically, what you could do in this example is realize that malloc is called in a lot of libc internal functions. A lot of them use it under the hood, and we just don't really think about it when they do. The main example that I used for a few things is scanf. Basically, if you scan something that's large, it'll scan it onto the heap, and it'll just make a larger and larger chunk as needed for serving this input string, and then afterwards it'll free it or whatever. But basically, what matters though is if you call a scanf with like a massive string of like well over hex 400 bytes, it'll make a large chunk, and when it makes this large chunk, then it'll actually end up calling malloc consolidate when this chunk is created and then freed. So by doing this, you still can consolidate your fast bins into the unsorted bin. And you don't actually have to directly malloc hex 500. You let scanf do that for you. And then you can free it again, like I said before. Yeah, okay. This is like, what if you don't have a use after free, like I said before? Then you can still bypass the check by putting the other one between them, like I said before. You can free chunk 0, then free chunk 1, and then free chunk 0 again, and it'll be fine. So the first allocation of chunk 0 will allow you to edit it, and then chunk 1 will be allocated, and then chunk 0 will be used again. So when it goes to that chunk 0 again, the edited information that's in the first keyword will be the list out of there. It'll be the pointer to the next chunk that you can choose to your own desire. So as long as you free something between them, you're fine. The double free check is very minimal. It just means you can't free it twice in a row, which is kind of greedy. So that's fine. What if you don't have a double free? What if you just have a heap overflow? Because we were talking about the 2 bugs earlier on. What if you had the heap overflow instead? Well, as long as you had like a big heap overflow, for example, if you had 2 chunks next to each other and the second one was freed into the fast bins, you could still overflow from the first one into the second one and overwrite that first pointer. And as long as you can overwrite that first pointer, you're fine. It doesn't have to be a use after free. It could involve another chunk. But what really matters though is that if you have this overflow, it's not like it matters. If anything, it's better than a use after free or a double free because you can just write into that chunk if it's next to it in memory. All you have to do is mess with one pointer and you're fine. So that's a very, very, very powerful attack. Okay, the next main attack that people used to do a lot, and still do, I don't know why I said used to, is an arbitrary free. So let's say the heap is fine. Let's say you don't have a use after free, and let's say you don't have a heap overflow even. But what happens is you have some other bug that lets you free whatever you want. Like maybe it overflows a character array on the stack onto a pointer to a chunk, and then that's freed. So in this case, the attack is pretty similar to a fast spin attack. It's only a little bit different. Awesome. See you around. Thanks for coming to the talk and all. So yeah, so free, arbitrary free. What do you do in this situation that makes it like a fast spin attack? Well, basically you can point your arbitrary pointer to be freed to a fake chunk in the way that we created a fake chunk with the fast spin attack. However, it's a little bit different in this case because of the fact that awesome. See you around. Because of the fact that in this one, there's a little bit more checks on the thing that we're freeing. It also checks if the bits are correct. Like it'll check if the is mapped or previous and use or stuff like that. Because free does more. It has to sort the chunk and put it in a bin and stuff like that. It has to know what's actually happening. So it doesn't just check the size. It actually has to be something valid, like hex 70 or 71 or 40 or 41. And there's also a check that the next size is actually also correct when you do it. If you free a fake fast spin and it sees, oh wait, the next size is like a billion or like some pointer, it's like, hey, that's not right. So there's a little bit more happening here. You can still free in any memory segment if you could pass these checks. All you have to do is find a fake chunk in memory or forge a fake chunk in memory, and then you free it. And while freeing isn't necessarily great, what matters is you can put your own chunk into the fast spin list. And then later on, when you're doing mallocs, eventually you can malloc this chunk. And then you can treat it as whatever your char array that you're mallocing rather than whatever it was when you forged it, however. So this is kind of a weird scenario. So I'm going to go a little bit into a scenario that this would be affecting, but the main thing that matters is that this is like a very important attack. It's not very easy inside of glibc, for example. I don't think there's a lot of very easily forged sizes and next sizes and valid bits and stuff, but it's still okay for other things, because if you have data on this stack or data or heap or whatever, you might have something where you have this situation with a valid fast spin size. The next size only has to be kind of believable. Like, I know that's kind of vague, but like there's a few checks it does. And as long as it's not like a negative number or something that's like super massive, it's fine. If it's like, it doesn't have to be the same size as the chunk. If it's hex 20, if it's hex 80, if it's hex 500 even, it'll go down. So it just has to be like semi-realistic. Basically, this is a good way to get into another sort of attack. Sometimes it's good to do something like a stack overflow. Sometimes it's good to do something like overwrite arrays to character pointers, maybe overwrite heap pointers that are stored in the BSS or stack. It's like a good primitive that leads to more usually. So you could even use it in situations to do something where you get overlapping chunks in the heap, for example, and then you could just do a fast spin attack on top of that. So because this one's kind of weird compared to the other ones, I'm going to go over some example scenario and why this actually matters. So let's say that we have an array of these structs in the BSS. It has a size and a chunk. That's pretty normal. You need to save your size with your heap chunk. So we have a long and then a character array pointer. So now let's say you can allocate it, you could free it, but you cannot edit it, for example. Okay, so let's say we had something like this. Let's say we had the name buffer in memory somewhere before it, and we had function pointer somewhere after this. Like these are all just global variables. let's say you could overflow the name buffer into this array of structs that we have stored in the BSS, for example. In this case, we could overwrite a chunk pointer and then free it. So another interesting thing here is that the size of the chunk that we allocate could be a valid size. We could have this be like hex 100 or hex 70 or something like that, for example. And then when you allocate another chunk of this size, we can get a chunk served in the BSS. And if we had a chunk in the BSS, we might be able to write into data that's in this function pointer list, like we talked about, these function pointers afterwards. Maybe we could overwrite these as like a character array. And then if we had like enough size, we could touch those and call our function, we're good. So that's a situation which House of Spirit might be useful, is when we have use of controlling integers in memory in a way to forge a chunk where we want to. It's very useful. When you see a situation which you need it, you kind of realize, oh, I can free anything. This is something like this. So these two primitives seem great. You can do freeze, you can do UF freeze, you can heap overflows a lot. Why would you actually need more attacks? Like I said before, sorry, my throat is dry. These are all fast bins, which means they have a pretty stringent size limit of like hex 80 for x64 programs. Sometimes you can't really allocate anything below that, like I mentioned. Sometimes you also have limitations on how many chunks you can have at a certain time. Maybe you could allocate 8 or 9 chunks and then you're done. Like it's like, oh, you can't have many more pointers than this. So sometimes you have to do another attack because of something like that, maybe. Also, you need the first keyword in your control. If you didn't really have control of the first keyword or two in like a struct, for example, you can't really do much with a fastbin exploit because you can't really overwrite the linked list in a way that you want to. So sometimes other exploits might be better for other situations, and that's why a lot of other ones matter. But if you have a very lenient fastbin size character arrays and stuff like that, this is like optimal. Okay. So now, another really old exploit is called the unlinked exploit. Basically, what happens is that you don't have to necessarily have a small bin. You could use unsorted bin to do something like this as well. But what really matters is that it's some doubly linked list. What this unlink macro is, and this is pretty common in like data structures and stuff, is that it removes an element from a doubly linked list. And because of the way that it does this, this macro is very useful for exploits, and it's been used since forever. Like this was in like the original email probably that the guy sent in 2005 or so. There's more checks now that we're gonna ignore at this moment, but then later on in the PowerPoint, I'll talk about the newer things and go into those some. But basically, here's what happens when you free some chunks inside of glibc. First, what it'll do is it'll check the size, which we don't care about. This is new. Anything like malloc print errors are probably new. A lot of them are. But in the old times, in 2.23, it would get the chunk and it would find the offset of the previous chunk if it was not used when you freed a small bin or unsorted bin that was adjacent to another small bin or unsorted bin. And then it would unlink the previous chunk. And this AV is the main arena. That's the way it's passed. So if possible, it will consolidate the two and unlink it from whatever list it's in, so it could be re-put into a new list as needed, whether it be large bins, small bins, whatever it needs to. So these another thing to keep in mind is that not all bins actually unset the previous in use bit of the next chunk. I know Tcache for sure does, and I'm pretty sure fastbin also does not. But there's chunks where if you free it and then you free another one, it'll still have the number 1 on the next chunk because it's not a unsortable or unsorted bin sort of chunk that'll go into small or large next. It's not treated the same. So it has to be pretty large chunks to do this. So here's the macro here. Here's what happens. Ignore the checks again. Like I said, these are like super new. We're talking about 2.23 at the moment, but this is what happens when you unlink a chunk from its doubly linked list. The main macro is it'll go to the forward pointer and then look at the back pointer of this chunk. So it'll go forward pointer being the, I don't know, I think I say it on the next slide or one of these. Okay, yeah, the forward pointer being the first keyword inside of the chunk. And then it'll go to the back pointer of that, so it'll add hex 18. And it'll set this value to be the back pointer of the current chunk. And then it'll do similar to go to the back pointer, which is at hex 18, go add hex 10 to that, and then write the forward pointer to this value. Basically what this does in an ideal situation without any use after freeze is it removes a chunk and it makes it where the previous one points to the next one, next points to the previous. It's like it was never there. But as far as like an exploit, like looking at it, if you have control of this and you can write to P forward and P back, what you have is the ability to write a pointer to a memory location to another writable memory location and vice versa. And that is very useful because you get 2 writes of basically whatever you want. And that's pretty massive. But they both have to be writable because it writes into the P back and P forward. So you can't just write something in like an executable section that's like RX into like the stack, because then when it tries to write back, it'll segfault. But it's still a great primitive. So let's say you have a use after free in a small min-sized chunk. Let's say you can't do fast bin. You know, the chunks are like massive and thick. So there's no hope is lost. We still have this unlinked macro. And again, let's say that they're char arrays. So let's say we have a chunk pointer in the BSS that points to the name chunk, and that's a character array. So when we abuse this unlinked macro, we can write a pointer to the malloc hook in this area in the BSS, because the malloc hook is in writable libc, the BSS is writable because it's variables. However, when you do something like this, you do want to keep in mind that the forward and back are offsets inside of the struct. It's not like it'll just write directly one and the other. Forward's at offset hex 10, back's at offset hex 18. You need to subtract a little from the area you're trying to write to. But either way, it's still a great primitive. And like I looked at before, here's what a chunk looks like as far as like the bins are concerned. You got a previous size and a size, and then we have the forward pointer and backward pointer. And then for large bins, which we'll go into, there's the next size and previous size. Like how I said, there's different sizes in large bins. Okay, can you get an arbitrary small bin? We notice we can unlink it, but how do we like get our own actual small bin that we can write into? Yeah, you can, but it's not nice. It's a really, really unattractive attack. It's pretty difficult. Because it's a doubly linked list. You have to put a new chunk into the doubly linked list and have it be referenced and have it validly do the linked list. So that's not always a very simple situation like the fast bin one is, where it just points away until nulls. If you can do an unlink attack, I would definitely recommend doing that over the arbitrary small bins, but it's definitely possible. And here's how. So for House of Lore, again, the forward and back pointers are used. Also, I know it's getting pretty late for a meeting and stuff. People can definitely leave when they want to. I understand. I'll definitely be putting it on YouTube afterwards. Okay, so for the House of Lore, again, we're doing the forward and back pointers, similar to how we did with the unlinking. But in this one, instead of unlinking a fake bin, we're going to overwrite the back pointer with our fake small chunk address. So in order to do this, again, we're going to need a valid size like we did with the fast bin, where it can be like, hey, this looks like a small bin, this will work. But it's also more difficult because of the fact that it'll check stuff like the next size, as well as stuff like the linked list pointers there and things like that. So you need, in a situation like this, for the small bin's forward pointer to point to the heap chunk that we are creating here, the one that we are overriding. It needs to point back to the linked list. Otherwise, it'll be like, hey, this chunk doesn't even point to you. Like, this is not valid, and then it'll fail out. So it requires a lot more forging of pointers and leaks and stuff. It's not the greatest attack. And then what it'll do is it'll fetch your bin from the small bin eventually. So as you saw, as like you can see here, small bins are allocated from the head of the small bin, and then it'll just follow the back pointers slowly until it reaches your bin, or until the head points to the head, in which case it's done. There's nothing left we can allocate. By corrupting the small bin back pointer, we can put our fake chunk into this list as long as we do not corrupt this doubly linked list. And this is where the back forward equals victim check happens. And this part is pretty monumental, but what happens is if we can do that, we can put ourselves in this list, and just like the fastbin code, eventually by following all the back pointers, we will end up serving our chunk as our char array. Okay, this one is the unsorted bin attack. This is one of the other primitives that are from the olden days that are still used a lot. And this one was like a very confusing attack when I learned it. I learned this before small bin stuff too, I should point out. But I think when I first saw this, I thought it was stupid. But then when I saw some of the situations in which it could be used, I was like, this is actually like ingenious. This is crazy what you can do with an unsorted bin attack. And I think that was sort of when I was like, okay, I really want to learn Heap exploitation, was after seeing some attacks that used stuff like this. Basically, this is like a pretty simple primitive. It's very similar to the unlinked one in a way. But what happens is the unsorted bin is a doubly linked list of recently free chunks that are not stored appropriately yet, like I said. Once an allocation is done that the unsorted bin cannot satisfy, they all go into smaller or large bins. So if you have an unsorted bin that has chunks of size hex 300 max, and then you allocate something of size hex 400, it's like, oh, we can't really help you there, but we can put these bins away. I don't know why it does that, but that's just how it works. You can also serve from the unsorted bin when chunks that are smaller than it or the exact same size. If you have an unsorted bin chunk of size hex 200, you can allocate anything up to hex 200 and it'll pull it out of that unsorted bin. So, I'm going to give some of the code, so I'll explain how the unsorted bin attack works. And I'm also going to give people a chance to look at it if they want and try to see which thing we would want to overwrite in it, which are the pointers inside of our structs, assuming we have a use after free and unsorted bin. That would give us the ability to write anywhere in memory, basically. What would you do for something like this? So here's the code. Anyone can type it in the chat. Basically, a little bit of context though. AV is the main arena. Unsorted chunks is just getting the head of the unsorted bin. Back at this point is just the back pointer of the current unsorted bin inside of the heap, basically. And then this is reached basically what happens if you allocate something that is larger than the unsorted bin, for example. If anyone can think of like what we should overwrite inside of our bin. And you give like maybe, I don't know, 10 more seconds. I don't know. You don't have to answer either. I was just thinking like if you wanted to try to take a jab at it. No, I understand. It's like kind of confusing. Yeah. Okay, so controlling the back one would give us the ability to write into av.back. Yes, that is actually correct. And also, if we control back, what we can also write is this back.forward, we will write this unsorted chunks AV, which is the libc pointer. So it's a very, very good thing to overwrite the back pointer inside of the unsorted bin, because doing that gives us the ability to not only put our chunk into the unsorted bin in a way, but it also does this code here, which does --forward equals unsorted bins AV, which basically is just putting a libc value, the unsorted bin value, anywhere we want in memory. And when I first learned about that, I was like, okay, that's not much. It's just a random large value. But basically, like I said, yeah, we can write the arena's unsorted bin address to an arbitrary location by controlling the back pointer. In the weird way of working in glibc 2.23, it doesn't really verify that this next unsorted bin that we put there in the previous is actually really valid. If our new chunk is the same size as the unsorted bin chunk, it will retrieve it to us eventually if we do pass any sort of checks. But the main purpose of the unsorted bin attack, because of the fact of the way it's used, which is not really to serve as much as just link chunks to other chunks, is that it does write this large value there. Once you do this, is your unsorted bin okay? No, your unsorted bin is no longer usable. You will have this fake chunk, and eventually it will realize it, and it'll call you out, and it'll crash. It'll not be good. But what matters though is that we can write a large value in memory, and usually when I do an unsorted bin attack, because of the fact that the unsorted bin will have some chunk that we don't want because of this AV back equals back and all that, I get all my chunks ready. I get them all allocated. I do not want to allocate anything from the unsorted bin after this, or anything larger than the unsorted bin, because the unsorted bin is no longer good. It is bad. But it's still a good attack, and I will show why. I'm probably hyping it down too much. Okay, so here basically is a little example code. First, I disabled standard out buffering, like I mentioned here. Normally, standard out, when it does printing, it'll sort of create a buffer on the heap. And I didn't really want this extra heap activity. I knew that my unsorted bin was destroyed, and when I printed here, it triggered my unsorted bin, and it was bad. So I disabled buffering for this, basically 1 byte at a time. So first I malloced 200, and then I set up some padding, and then I freed the first chunk. So that is now in the unsorted bin. So then what I did was I set the 1, which is the second keyword inside, to be val -2. And because it's a UN64, that means it's hex 10 bytes before val. And what hex 10 bytes before is that it is the, back here, it is the forward pointer of this back. So, because it's the first forward and then back. And then what I did was I alloced 200 to remove my chunk from this unsorted bin. And as long as it's the same size, it won't really trigger any errors right away, because it'll just pull this one out of the unsorted bin, do this write thing, and then put whatever the back one is into the unsorted bin. But at least, like, for now, it'll succeed. And then it'll print, and then I chose to print the value. And I initialized to 0. I don't touch it anywhere else except writing the address somewhere. Let's see if it changes. Yes. So when I ran this and compiled it and all, this value here, as you can see, is 7F something something. It's a libc leak. Like I said here, libc leaks usually start with something like 7F. Heap leaks usually start with something like a 5.5 or 5.6 maybe. But basically what matters is it's not 0. We wrote this really large value here. And this value is the address of the unsorted bin inside of the main arena. So, wait, let me see. Why is it address of val -hex2 instead of val? Okay, so basically what happens is that chunk 1 will contain the previous and then the next and then the forward or whatever. I don't know. I'm wording these really badly. Okay, forward and then back. And we're overriding the back pointer. So what happens is we're forging basically a fake unsorted bin at this pointer. But what matters is that here it's writing back forward. So let's say that val minus hex 10 is the address of our fake chunk. It's writing the libc value into the offset of fd into this structure, which is the hex 10th, because first previous size, then forward, then back. So the problem is that when we're trying to do this primitive, we have to subtract that value because it's going to be writing not directly at the beginning of the structure. It's going to be writing it at the structure plus hex 10, which is the forward element of the structure, which we can see back here. Yeah. So here is FD, and it's going to basically have the malloc chunk is what our val is. So we need to write it at the hex 10th. We need to ignore previous size and size. Does that make sense? Yeah, it's actually val minus hex 10. C is just really bad. I was struggling with that when I compiled this program. I was struggling with that for a long time. But yeah, it's a UN64 address. So 2 times hex 8 is the hex 10. That's the issue. I was trying to cast it to a character and then do minus hex 10, but it was not letting me do that. But yeah, that's the issue I was having. Yeah. Okay. So yeah, why does this primitive really matter? We're just writing a large value somewhere in memory. We're writing a libc pointer. Usually it's like sort of a middle point, like a little primitive that leads to other primitives. One of those being House of Orange, which I'm going to describe, but there's a few. The other thing is that this libc pointer that we write doesn't actually have to be aligned. We can use this data to go somewhere to do partial overwrites. And also, the libc pointer is only 5 bytes large. So we have 3 null bytes that also get written. We could use this to write null bytes into the lower ordered bits or bytes of memory in order to do this attack as well. So that's also something very useful. But the main way that I think is cool to use this is because you can attack something called global max fast. And what that is basically a check that when a bin is freed, it'll compare it to global max fast. And if it's less than that or equal, I guess, then it'll be like, okay, this is a valid fast bin. And then it'll put it into the fast bin array. If it's larger, it'll put it into unsorted bin and let the unsorted bin later do whatever it has to with it. So if you can overwrite global max fast with a large value with the unsorted bin attack, suddenly everything's in a fast bin. We could treat any size bin as a fast bin, and it'll just make them all singly linked lists for us. So what you can do with the unsorted bin attack is you can free it into the, or use the unsorted bin attack to overwrite the global max fast, and then you could basically just free whatever else you've allocated. If you're not doing a fast bin attack, let's just say we can only allocate stuff like size hex 200 maybe. We do our unsorted bin attack, and we already have some chunks ready of size hex 200. If we free a chunk of size hex 200, it's going into the fast bin somehow. It's not going in, it's going to the fast bin for size hex 200, which doesn't really exist, but it's going in there anyway. And then when we allocate for size hex 200, it'll pull from that fast bin. So once we do this attack in global max fast, we don't have to worry about any other bins. This is like basically setting up to do a fast bin attack now. The last one that I didn't really go into much yet is large bins. They are the worst by far. Basically, large bins involve 2 doubly linked lists, like I talked about. There's a linked list that involves libc pointers, which is if it's like the previous and next. And then there's also previous and next sizes, because the large bin has a range of sizes in each chunk. You can still do attacks with them. You can still corrupt them and do attacks, but because of the fact that there's 2 linked lists, it's a little bit alarming. It does a lot of checks on both of them, and it follows both of them when it's searching for other large bins and stuff. It's kind of scary, but there's definitely attacks you can do for large bins if you have to. Like I said, there's 2 linked lists. First one is for chunks of the same size, and then the next linked list is for chunks of different sizes that fall into the same range still. And this is the logic for large bins. It's a lot. But basically what happens is that they're stored in a sorted order inside of each of the indexes. So it'll have ones of like size hex 40, and those are all linked. Like if it's like, let's say it's stored ones from like hex 1,000 to 1,010 somehow. So or 1,100. This is probably not true, but if you had a chunk that did that, then it would first have a linked list of all of them of size hex 1,000, and then if you had one of size like hex 1,050, that would be in the next size, and then that would have anything of that size, and then that would also link back. So you can imagine it almost as like a 3D map where it's like one size is like a circle, and then there's like another circle going to each of the different sizes. It's a little bit confusing, but that's basically the gist of it. So for a large bin attack, in 2.23, you could actually choose to corrupt either of these lists if you wanted to. In later versions, you can't. I'll probably go more into that later, I believe, but basically later on, you can only attack the previous size, and it basically becomes the unsorted bin attack just on the previous size, previous next size, back next size right here. That's the only pointer you can attack now. But in 2.23, you could attack both linked lists. So if you corrupted the previous and next sizes, like I said, you get a primitive that's pretty much like the unsorted bin attack. It'll unlink your size from the linked list, and in doing that, it'll write a large value as it writes to the previous size. However, if you corrupt the main linked list, you can also do something that's kind of like House of Valor, where we made the fake small bin. You can make a fake large bin as well. However, it has 4 pointers inside of it. You kind of have to forge them into something that passes the checks, and that's a lot. And I didn't want to talk about all of that because the large bin attack alone could be like a full everything. But what matters though is that like it's possible. It's just not easy. For if you want to see what it looks like in action, Zero CTF 2018 had this challenge called Heap Storm 2, and it blew my mind. It was crazy. It was a large bin attack, and I'd never done a large bin attack before, but it uses the large bin attack for some very interesting primitives because they had to use large bins. And I'm not going to discuss it all here, but I do recommend people look at write-ups for that. It's very interesting. Okay, so what's left? What if you could only corrupt metadata instead? Because all the bugs so far involved editing data inside of what did I do here? Inside of free chunks. Inside of free chunks, I'm dumb. Whether it's like a use free or some heap overflow, it's like really large. But sometimes you can only do a small overflow. And in a lot of cases, you can only really overflow the chunk header, which includes the size and previous size, and you can't actually touch the forward and back pointers. So, and for this, it's pretty important to understand how heap chunk headers actually work. So the chunk header has the size, which is hex 10 bytes aligned, but it also has these 3 utility pointers basically, and utility bits. So this one, the first bit is previous in use, like I said before. And so if it's like hex 70, the chunk before it is freed and can be consolidated with. If it's hex 71, then it can't. Then there's the is mapped one, which basically means if mmap serves the chunk to you, then this one will be set. And then the non-main arena one is set if it's obtained for like another thread with a different arena or anything like that that could create a new arena. So we're not going to worry about the 2 and 4 much right now. These are kind of confusing. We'll go into them later. But for now, the previous and use bit is like the main one that we do care about. So generally, the goal in overriding heap metadata, mainly like the size and the previous and use bit, is to actually end up making overlapping chunks in memory. Because once you have overlapping chunks, if you free one and then edit the other, you basically have a use after free. It's not the same chunk, but they are overlapping in a way that you can edit one's information pretty much completely. Then you could do a fast bin attack. You could do whatever you want, basically. So that's usually the goal, is to reach these points at that instead. However, these bugs are like very, very, very common. Probably more common than use after freeze in some scenarios. Sometimes you can only override like one keyword. Sometimes you can only overwrite 1 byte, and in other times you can only overwrite a single null byte. Sometimes it just terminates your string in a way that writes a null byte into the size of the next chunk. And that's very easy to miss when you're programming. And it's also something that you can use to get a fast bin attack. So that's pretty crazy. Okay, so first we'll talk about creating overlapping chunks by making your chunks actually larger. So let's say that we have 2 JSON chunks in memory. Each one is size hex 200, for example. And we free the first one. Now, if we have a bug that allows us to edit the heap metadata, we can actually change the size to be hex 410. I say 410 because there's like 10 bytes of the second chunk's header, for example. And then if we malloc a chunk of size hex 400, it'll be like, hey, we have a unsorted bin here of size hex 400, even though it was theoretically only hex 200 when we freed it, but it doesn't know that. It'll still serve us that chunk. And now this massive chunk we have will also overlap with the second smaller chunk that we had that was chunk 2 of the initial 2 that we created. And this is interesting because they're both in use now. And once we have 2 chunks that overlap into in-use area, we basically win. Because at this point, if we free chunk 2, we can edit it with this new chunk we made. I'll call it chunk 3. And then we could overwrite the pointers. We can overwrite the header again. We could, if it was smaller, we could do something like fast bin attack. There's like a lot you could do by having these overlapping chunks. That's always the goal with the heap metadata attacks in the most case. Do we have to overlap with real chunks? No, not really. We could always basically make fake headers in the heap. That's not anything that was not able to be done. So let's say in this case before, we had the 200 and 200, and let's say we overwrote it with 300 for some reason instead. But if we have a fake header 300 forward in memory, so like about 100 forward in the second chunk, it'll still work as long as the header looks kind of valid. So if we have it be like previous size hex 300, next size hex, I don't know, 21 or something, it's like, yeah, okay. And then it'll still let us allocate a chunk of size hex 300 from this unsorted bin. So that's really interesting, is that we can still fake our own headers and stuff. We don't actually have to overlap with real chunks. It's kind of funny. Okay, so now consolidating backwards. For this one, I'm going to basically talk about like the null byte overflow. That'll basically work if our chunk is of like a thing like hex 100 or hex 200 or something. It'll work in other cases too, but that's like kind of ideal. So there are variants in which you consolidate backwards with a fake unsorted bin. That's going to be kind of like what I'm talking about now, but I'm not going to talk about that specifically. You could forge an unsorted bin if you had leaks, but that's not anything good. And also, like I said, it's better if we have a size like hex 100 or hex 200 or something. But if it's bigger, we'll just lose part of our chunk. It won't actually hurt us that badly. We'll have to forge a header at hex 100 and lose part of the chunk, but we wouldn't gain anything from that. So the interesting thing about a null byte overflow is that, like I said, we're possibly decreasing the size, but more importantly, we're unsetting the previous in use bit. And if we unset the previous in use bit and then free, it'll be like, oh, the chunk before me is also free. I might as well consolidate. And then it'll follow the previous size, which we also overwrote because of the fact that we had the null byte overflow. Let me find a heap thing in here really quick. I feel like I should have a screenshot of heap memory. Maybe I don't. Okay, but what matters though is that when we're using chunks, and this part is kind of finicky, I don't know why it works like this, but if we're using a chunk that has like a header with like previous size and then maybe hex 40 previous in size, we can actually use hex 48 because when the chunk is in use, there's no reason to actually worry about this previous size. But when it's freed, that actually becomes something that's used. And that's very weird to me, at least. But so when we're allocating a chunk that we do a null byte overflow in, we want to allocate a chunk of like hex 28 or like something 8 because of the fact that that'll put us where the null byte overflows into the size of the next one, and the last 8 bytes is actually the previous size of the next one. And it makes more sense in memory probably, but that's something that you want to keep in mind. So when you unset the previous in use and free it, it'll consolidate backwards. And what you want to do is you want to forge a fake previous size to point to another unsorted bin in memory. But the interesting part is that, at least in 2.23, you could have unsorted bin, chunk in use, chunk that you overflowed or whatever. Or I guess you could have those be the same thing. So unsorted bin, in use chunk that you overflow, and then next one. And if you overflow it and it points back to the first chunk, it'll consolidate all that area into one large unsorted bin with our in use chunk in the middle of it still. And that is the part that becomes very weird, is that we could create the overlap because of that. Then we just allocate it, get our use after free, and then we could do whatever. We could do a fast bin attack for sure. So here's some code to basically show what that looks like. I create a chunk of size AO, try as a chunk of size hex 18, and then F8. F8 is going to be hex 100 because of the header, and then of size hex 10 just for padding. So first I free the first one, and it's large enough that that will go into the unsorted bin. Then I overflow. I set the previous size in chunk 2, which would be the third, I guess, index 2 keyword, to be the size of the first chunk, and then the size of the second chunk, and then the 10 for the header between them. And then I overwrite the null byte there. It's kind of an artificial example. I put the null byte at the final offset inside of chunk 2, which is 1 out of bounds. Then when I free chunk 3, it'll realize that the previous in-use bit is not set anymore. It should be hex 101, but because of the null byte, it's hex 100. So it'll be like, okay, cool, let me consolidate backwards. It'll see the previous size and look up there and see our unsorted bin pointers and be like, this is perfect. This is exactly what I need to unlink with. And then it'll unlink there. So then if I malloc size hex A0, it'll overlap with chunk 1. I malloc hex 18, it'll overlap with chunk 2. But I never free chunk 2. That's still in use. So I showed here, you can string copy something in chunk 5, print it with chunk 2, and the numbers will be the same. Or I guess the string will be the same. So I compiled this and ran it, and it said, did I land this? And yes, I did, because it didn't crash somehow. So that's a very useful attack that shows how the smallest bug can give us such a good primitive. Just one null byte overflow gives us this. And at this point, like, we have overlapping chunks of hex 18. We could do a fast bin attack. And if they were of size hex 68, then we could do the one in the libc with the main arena. Like, this is a massively powerful attack. Okay, the other thing you could do with the null bytes is this thing called the House of Einerjar. I don't know who necessarily made it, but it's kind of like the other one, but you need leaks. And what it allows you to do is forge a fake chunk anywhere in memory if you can write there beforehand. For 2.23, you can do it anywhere. 2.32, they have checks now, so that you can do it on the heap, but it checks system mem and stuff like that, and then it'll fail out if you try to do it anywhere else. Sorry, okay. Why was chunk 3 back size hex 180 and not pointing to the hex 18 chunk? Okay, I should have shown this in memory in hindsight in a debugger. But basically, what it'll look like is the first one is going to have, and I'm going to do like 2 rows of like keywords, basically. The first one is going to be hex A0, and it's basically just the full thing is a bunch of data. It doesn't matter. And then the hex 18 is the one we overflow. So what that'll do is it'll have the size, which is going to be hex 21, and then 3 words of memory slots, I guess no, 5, because it's size hex 21. And then the size for the hex F8 chunk, which is going to be hex 101, will be next. But the interesting thing is that, let me go back to this. It'll make more sense when I look at the struct again. Yeah, here, what happens is when we malloc a chunk of size hexa, okay, see here, when we malloc a chunk of size something that ends in 8, this previous size is not used by a chunk until it's freed. So what happens is this only matters if that chunk is freed. So if we have like hex 68 or hex 18 or something, it'll serve us this data as part of our chunk. So the first hex 10 bytes will be wherever, but then the hex 10 through hex 18 bytes will be at this previous size here. And then mchunk previous size is right inside the user portion. Yeah, it's at the exact end of it. So if you imagine it as 2 rows, we have hex 10, and then like, let's say it was hex 30. We have like hex 10, 20, and then if we were going to do 28, it would take the previous size location of it. If we make it size hex 30, we can't overwrite the size. The size is needed for all chunks, so it'll just move the header down a row. But if it's a size that ends with 8, we can actually write our own data inside of this mchunk previous size. So that's what I did here was I allocated a chunk of size hex 18, and because of that, this keywords 2, which is I cast it to a UN64T, so it's the hex 10 inside is where the previous size of chunk 3 would be if chunk 2 was free. Because chunk 2 is not free, it shouldn't matter, but because of the fact that we did the null byte overflow, it assumes that chunk 2 is free, and it assumes that this chunk 2's last keyword is the previous size of chunk 2. Does that make sense? Yeah, it's because of the fact that we did set the previous and use size, yeah. So the null byte overflows, the only goal really is to unset the previous and use. And then it'll be like this chunk before me is a bin, and it'll end in a previous size. But in reality, it's not a bin, and it can end in whatever we want it to end in. So yeah, that's why the null byte overflow works the way it does, is by forging the previous size. Yeah, so the difference between that attack and then the null byte attack for House of Einerjar is that you can set the previous size, at least in 2.23, to be anything. It could be massive. So theoretically, you could have a fake chunk in the BSS, for example, or even libc. And then if you set this size to be so big that adding this previous size that you forged to the pointer to the next chunk, it'll actually be in another memory region. And as long as it looks like you have a valid unsorted list there, then unsorted bin there, I guess, then it'll be like, yeah, sure, we can unlink this. And then you can allocate memory there. So that's a very cool attack. Can the pointer underflow? It could in 2.23. In 2.23, you could set it to be anything because it did just add them in x86. It could be like add this byte to this one, and it was 64-bit. And I believe that because of the fact of the way it did it, I'm pretty sure you could do it unlinking something like the stack or libc further in memory. I don't think that it didn't check carry bit or anything like that for sure. So you could definitely underflow the pointer. You could do it with anything. Now it realized, hey, this previous size has to be valid. It has to be less than system mem, which is the max size a chunk can be. Because if it's more than that, like it's obviously not right. It's like something's wrong here. So that's a check that they added later on. But I'm almost positive that you could do a pointer underflow with it. I feel like I've seen that before. So this is a good way to basically get an arbitrary chunk of memory anywhere. And it's also very similar to another attack that involves getting an arbitrary chunk with a massive number, which is coming up right now. The last thing we can corrupt that I didn't really talk about as far as like 2.23 exploits is that the top pointer. Like I said, the top chunk is basically just a massive unsorted bin almost. It has like a size. You can take out little bits off of it and leave the rest there. But you can still overwrite the size of this top chunk if you had a overflow. So there's one major exploit that involved this. And there's also House of Orange, which is really kind of weird. So I'm not going to talk about that until I talked about the FSOP stuff. But that's like the gist of this here, is that we can overwrite the size of the top. So like I said, some people call the top the forest or the wilderness. It's probably the wilderness actually. So here's two code snippets, 2.31 and 2.23. This is the new, this is the old. I should have done it the other way. But there's one check that was added, and that check shows a very interesting attack that could be done. I want to see, like, if anyone wants to take a guess at what we could do by overflowing the top size. It'd be really cool to see if anyone could guess that based on the check that was added, at least. And also, like, if you want to, you can keep in mind the previous attack, the House of Einerjar, because it's also quite similar. But I'll give like maybe 20 seconds, see if anyone wants to guess stuff. Awesome. See you around. Yeah, it's a long presentation. I didn't realize how long it was going to go for. So yeah, what could happen? Oh yeah, 135. That means I'm over halfway there. Yep, you can jump out of the heap if the size is big enough. Yeah, if the chunk size is massive, then you could basically malloc anywhere in memory. So that is basically the gist behind the House of Force. In 2.23, you could set that size to anything you wanted. And as a result, you could theoretically make it insanely massive. Let me see what Claire said. If you still have a lot left, you can schedule a part 2 if you'd like, so you don't have to cover everything tonight. I mean, that's up to everyone else if anyone else wants to hear it. I could keep going or do it another day. I would definitely greatly appreciate if I could like have a slight intermission to grab water or something too, but we'll see. Basically, after I go over House of Force, dang, no breaks. Dude, I'm drinking soda. I made the mistake. I was like, I'm gonna get my mouth dry. I'm gonna get a Dr. Pepper. Stay hydrated. And I also do have to use the restroom too. But basically, after House of Force, I'm gonna go a little bit into FSOP in the amounts that you need to do any sort of heap exploit, and then I'm gonna go into Tcache and then how to do some of the exploits on newer versions with more checks. And then I'm going to call out a few different attacks I've seen people do. I'm going to talk about House of Red, House of Corrosion, and then the one that HK did too. There's a couple of really cool ones. And yeah, I feel like the first part is probably the biggest part though. I think we're already like getting there. But does anyone else want me to marathon it out? I don't mind. I would take a like 5-minute break if I did though. You'd go for a part 2? Okay, yeah. I mean, also I could always just film the rest and then splice them together for like a YouTube video or something too. Whatever works. It's up to everyone else. I'm a man of the people. I don't know where my Zoom is. Okay, yeah. I'd be down to do a part 2 for sure. I don't mind. I don't mind at all. If everyone wanted a part 2, I could always do a part 2 during like the reading days because I'm sure everyone wants like, I don't know if we had a lot of stuff planned for then. And it's also going to be like relatively shorter than this one. But I don't know. It's up to whatever anyone else wants.
The only event we have left is elections. So you have a lot of flexibility for when you want to host it. So if you want to do it during reading days, that's totally fine.
Wait, is an election next Thursday?
Yes. Yes, it is.
Okay.
Which I believe is one of our reading days.
I mean, I could also do it if anyone wants to watch it on a different night or something too. I could do it on Wednesday when we have our cyber ranges, just grind out the second part. I don't mind at all. Also, did anything make sense? Like if there's anything that people don't know or that's kind of confusing, you can ask it in the chat now or say it aloud because I can answer any questions. I want to help. How do you solve breakout on TW? I haven't gotten there yet. I'm not going to say how to though. No way. I will say probably that after I do both parts, I think that people should be able to solve every TW challenge is what I'm hoping for. I don't say like, oh, this works for this challenge and this works for this challenge or stuff, but like, I think I kind of talk about every attack I've seen at least. How do you make chemical shellcode? I don't even know that one yet. I have not done that one yet. I'll be honest. I think the real question is there a WASM heap? Is there a WASM heap or not? I don't know where my Zoom went. I lost Zoom. What? Oh. How do you do this? Zoom is so weird. Wait, how do you get to Zoom again? Stop share. Okay. They had a WASM shellcoding in 0CTF with WASM inside of WASM. That sounds really bad. That sounds really painful. Dang. I remember I did a challenge for Blaze CTF a while ago where you used WASM to overflow a AES key, and it was like a pwn/crypto thing, and it was kind of weird, but it was cool. I really want to learn Mac OS Heap. That's the one I have not done yet. I saw a few challenges on how Mac Heap works. I think that'd be cool. I've done a little bit of Windows. I know how LFH works minimally. Cool. Yeah, we can definitely do a part 2. I know it's getting late. Yeah. If there's anything I did wrong or that I missed or anything so far, people can definitely let me know, and then I'll try to fix it up in the PowerPoint. Like the one where I said fast spins were doubly linked, I was wrong. But if there's anything else like that, it'd be super cool if people hit me up and said, "Hey, you did something dumb." So I'd like to know. Yeah, dude, I need a new editor. Matt didn't catch that one. Oh, yeah, no, that was on purpose. The hex $8. I put that there to show that it has to end in 8. I didn't mean that it has to be 4-8. I was like, oh, it can be anything that ends in 8. I don't know. I didn't know a better way to type that, so I just said, oh, yeah, if you're doing the null byte overflow, it needs to end in 8. So any chunk that's like hex $8 works. I call it top, but I think I started calling it forest after doing the House of Forest. So I did forget it was called the Wilderness, but yeah, no, it is. I should remember that one too. Yeah, Wilderness is a long word. Top chunk is fine. I've done other interesting top ones. I remember once I did a fast spin attack on main arena at the top of it, like in the beginning of the struct, and I overwrote the top pointer, and I used that to write to malloc hook or something like that. That was weird. It was a really weird exploit. It was kind of cool. I also didn't get into the House of Mind yet, which is the one where you basically forge a malloc struct on the heap, and then create your own fake fast bit list in it. On the cool. So you could set where malloc. Yeah. Basically, you could overwrite the top chunk and point it anywhere, and then if you call malloc, and it doesn't know where to get it from, it'll just get it from there, and it'll move the size down. It doesn't even check the size. Yeah, it doesn't check the size at all. I don't believe. It's incredibly OP. As long as your chunk is of a normal size, it's probably fine. Yeah, I think Rob showed me that. We were working on a challenge for Geek Phone, and he was like, "Oh, yeah, you should just attack main arena top." And I was like, "Oh, that's good." Yeah. Cool, cool. When should I do the second part? When do people want that? People can vote on it in the chat. I wish I was on Twitch right now. I think that'd be cool. I'd be able to do it any Thursday. Next 2 or 3.
Well, the only thing is if we do it the Thursday after elections, that's going to be right during exams. So you probably don't want to do it then.
Yeah. I mean, I could also do it a different day of the week because.
Yeah, I think you might have to.
Yeah, I didn't realize there's only 2 weeks of school left.
Yeah.
Dang. I didn't finish my senior project.
You could do like a Wednesday or a Friday of next week.
I'd be down for that. Because yeah, reading days are Thursday and Friday, and I don't really have anything then, so I don't have any reason not to give it on Wednesday either. I think that's good. I'd be down to do either of those. We can have people do a vote in Discord.
Okay, yeah, that'll work. Do you want to do it like same time of day, like as the GBM, or is there a better time?
I can do it anytime that works. I think if everyone, this time is probably good for most people because it's like after classes and all, so I'm good with that.
Okay. Yeah, we can have a poll in Discord and Slack and see what people say.
Cool. I'm good with that.
All right. Well, thank you so much for giving this talk. Mm-hmm. This is not a topic that we would have anyone else present on, and I really appreciate how deep you are going with it.
Yeah, I want to leave as like a good resource for the club after I'm gone, so they can pick up and learn Heap if they want to.
For sure. I'm gonna stop the recording now because it's been going.
Yeah, cool. I'm good with that. Yeah, no problem.